enthalpy. Enthalpy, this term is to measure energy, that's stored within a substance. For example, as in petrol, methane, wood, they all can produce heat energy. And this heat energy, but they are of different amount. What do I mean by that? Let's show you. Say if I have petrol, methane, and wood, they all can burn and release energy. And okay, now when they burn, what will happen? Yes, petrol will release energy. And how about methane? Look, they release energy too. How about wood? Yes, they release energy as well. So you will see that the energy, yes, they all release energy, but they are of different amount. Petrol, they release a lot more energy than wood. That's why we will prefer to use petrol, because they have more energy content than wood. Because if you're burning the same amount of substance, one's petrol will give you a lot more energy than wood. Okay, so what we pay attention is onto the energy now. To measuring energy that's stored within the substance, we're using enthalpy to measure. As you see, the high enthalpy, like for example, petrol, you will have higher enthalpy, or substance, anything with lower enthalpy. Of course, on the higher it is, the more energy inside. The lower it is, that means less energy inside. And now let's see how this enthalpy work to measure energy. I'm using the same graph of petrol, methane, and wood. And how do I represent the energy content? Okay, petrol, when they burn with oxygen, they release water and carbon dioxide. Methane with oxygen also release water and carbon dioxide. Wood we burn with oxygen also release water and carbon dioxide. But we know that the energy are different. One will be a lot more than the other. How do I represent it onto a enthalpy graph? In this enthalpy graph, petrol, in the beginning, you have very high energy. You have very high energy content. So you can see that I put it right up onto the very top. And when it burns, the energy release. The energy release, and now once you burn, it becomes carbon dioxide and water. Imagine, can you take the carbon dioxide and burn? No, because carbon dioxide and water is a lower energy content. They are at a lower energy content. So they have they don't have much energy in it now. Now let's look on to the next one, methane. Methane, they have energy, but the energy is lower than petrol. This is the enthalpy level. And methane, when with oxygen, that is how much energy they have. But when they burn, energy release, and it becomes carbon dioxide and water. How about wood? Wood have even less energy. So I represent on the enthalpy graph onto a lower level. And when they burn, they also release into carbon dioxide and water. And that's how we're using the enthalpy to represent the energy stored within the substance. So you can see on the enthalpy, the higher up, more energy. The lower down, less energy. Now we're going to learn an important term. The first term, exothermic. What's meant by exothermic reaction? Of this reaction, you will release energy. You will release energy. Example, as a petrol react with oxygen, you will form carbon dioxide and water. In this reaction, energy will release. Energy will release. Exothermic. Exo. Exit. Exit out. Release out. Release heat out. The next one, endothermic. Endothermics, endo, entry, enter, enter in. You will absorb energy. As substance, you have to add energy for the reaction to happen. Of this equation, you have to add energy for the reaction to happen. So, please learn this. Exothermic means it release energy. Endothermic means it will absorb energy. And now we're going to look onto the enthalpy graph of this endothermic and exothermic. Let's look onto the exothermic reaction, the ones that release energy. Exothermic. So on the enthalpy graph, as we say in the burning of wood. So wood, when it combine with oxygen and burn, it becomes carbon dioxide and water. In the beginning, this wood and oxygen, they have a lot of energy stored in it. And when they burn, this energy release out. And once they release, it becomes water and carbon dioxide. And this, so you can see it going down the hill. It going down the hill. And this is a exothermic reaction. So exothermic reaction, you will always notice they will be minus heat of reaction. And why that is a delta? What's delta H mean? That means delta means change. You change from here to here. So you're changing from this level down to this level. So in between, it is the changing. So, and this change, when you see a minus sign, means this is an exothermic reaction. It releases heat. So, as you see on here, you say on the delta H, that means in this change of heat of reaction, it is minus 120 kilojoules. What is minus 120 kilojoules? Minus means release of 120 kilojoules. Kilojoules is the energy unit. Energy. Now we look on to the next one. Endothermic. Endothermic, this reaction, you want the reaction happen, you have to add energy. Endothermic, you have to add energy, add heat for the reaction to happen. So example, photosynthesis. On photosynthesis, for example, water and carbon dioxide, you want them to become glucose and oxygen. In here, water and carbon dioxide is a low energy content substance. They have a lower enthalpy. So you have to using the sun energy. You have to using the sun to add heat. And now with the sun energy, it become a high energy content compound, glucose and oxygen. Become glucose and oxygen. So you form a low energy compound. You add heat, become a higher energy compound. So in this case, you see this change. This is the changing. And this change will be had to put a plus. You have to add heat. You have to add energy for the change to happen. So when you see this delta H, if you see you have to add energy, that means this is an endothermic reaction. It is an endothermic reaction. So please understand this concept well. If it is the difference of these two, pay attention onto this heat of reaction. This delta H, change of heat. So this, you say on this reaction is exothermic because it releases 120 kilojoules. In this heat of reaction, this is endothermic because you have to add 120 kilojoules. Please learn this concept well. And now we consider further. So far we learned to measuring energy. Now I'm going to talk about the molar heat of reaction. We just learned the word heat of reaction, but now we add the ones in front. Molar heat of reaction. Molar heat of reaction. What's meant by molar heat of reaction? The unit is something kilojoules per mole. Let me explain what that means. Imagine if you can see these two energy release, which ones have a higher enthalpy than the other? Then you say it's obvious. Must be this one have a higher energy, then this one must have a lower energy. Correct. Then you say, hey, how much molar heat of reaction? I say, okay, I burn that much of fuel, release that much of heat. And how about the other one? Oh, I just burn a tiny weeny little bit of fuel and you release that much of heat. Now, would you say which one give you more energy? Then you say, wow, this is not right. Look, you burn that much to release energy, but this one you only burn little bit and you will already release that much energy. So you will say maybe this one in fact will give more energy, isn't it? So you are not just only look onto the heat energy. You also have to see how much mole of fuel that you burn. S, how much mole of substance correspond to how much heat energy, kilojoules. So you consider to make measurement are not just only see the content of heat. The heat, you are not only look onto the energy, but rather you also look onto how much mole of substance they're burning. How much mole of substance that you are burning. So now let's give further example. Here's an example. If ethanol burn in air as according to the formula, give carbon dioxide and water, and pay attention. Here the energy unit, it release 1367 kilojoules per mole. What does this unit mean? You have a unit for mole of substance and the energy release. Look at here. The mole is talking about how much fuel, how much ethanol you burn. And 1367 is talking about how much energy when you burn this fuel, ethanol, and how much energy it's going to release. So pay attention of this unit. One part is talking about fuel of that substance. The other part is talking about the heat energy it released. Student, you may be familiar with this picture. Here I want to say, in most of the equation that you can analyze in ionic equation or half equation, but most of these equations have also one factor we didn't mention. They will have an energy involved. They will have energy involved. What do I mean by that? Let's look some example. If you look on some of the equation, like acid react with metal, or acid react with base, or combustion, or metal react in water, you find most of those reactions, they will either release or absorb energy. And in most cases, they release energy, in fact. So this I want to say is, now you start to see in most equations, you also will consider the energy factor, which is the kilojoules per mole. Now let's start. As on combustion reaction with burning fuel, here I have a table. You see, I put this minus delta H, how much kilojoules per mole. What's that mean? It means if I burn that much kilojoules, it will release energy. It will release energy. And you also realize I have many different substances. Methane, ethane, ethine, they have different substance. And all these substances give different amount of energy too. Some smaller, some bigger. And I give you two examples. One thing, on your burning on methane, that's happened into your cooking stove or your Bunsen burner. How much energy it releases? It releases about minus 891 kilojoules per energy. So, but if I burn a different type of fuel, you watch. If I burning ethine, and you look onto, they both burning the same amount, I both burn 1 mole, and you see the energy is a lot more, minus 1301. And what is ethine we commonly use for? They raise the temperature, they use it to cutting metal, melt to cut metal. So that is very, very high temperature. So here to demonstrate one point. Different fuel have different energy content in it. Don't assume you burn the things have same energy. Every substance have different content of energy stored within. And same apply. Now I'm going to talk about the heat of solution. When you put a spoon of salt into a solvent, you see they will have the temperature change too. And usually the temperature change will be smaller, and maybe you didn't notice. And now let's look onto the following example. Sodium hydroxide. If you put a sodium hydroxide in water, you will find they are strongly exothermic. Exothermic. What exothermic means? Exo, exit of heat, release heat. So this, you will find that they release heat. How did you show as exothermic? Minus that much kilojoules. Minus. And you expect this one will release heat like this. So if you put a spoon of sodium hydroxide in water and you touch onto the glass, you find it's getting quite hot because they release heat. But now I'm going to show you another opposite example. Ammonium nitrate. Of this ammonium nitrate, if you put it in water and you touch the bottle, it's getting cooler. You feel, oh, it's getting colder instead of getting hotter. Why? Because it absorbs heat. You absorb heat, and you see onto the change of heat of reaction is a plus sign, plus 25.7 kilojoules per mole, plus. That means this one they will absorb heat. You will absorb heat from the surrounding. So it will make the outside colder because you absorb the heat. So this is to demonstrate heat of solution will also have a heat change in a chemical reaction. Let's do another example, very common. Acid-base reaction. You put a bucket of acid, neutralize a bucket of base, and you know equation should form salt and water. Look onto this equation and look into the heat of onto this heat of reaction. It's a minus sign. What's minus sign mean? Exothermic. This is an exothermic reaction. That means once you put this in, you touch the outside, you find it's getting very hot. You're getting very hot because this reaction is an exothermic reaction. So student, understanding this concept of many equations that we learn, they do have a heat involved.